Okay, so in this unit, we are going to study thermochemistry, which is the study of heat that is used or released in a chemical reaction. So we're going to be looking at exothermic and endothermic reactions, but now we're going to actually calculate the amount of heat. So we're going to I'm going to talk real quick about the difference between heat versus temperature. So heat and temperature are different things. Temperature is an average of the kinetic energy of the molecules. So make yourself a note of this. Since it is an average, thermometers are not actually recording the individual temperature of all of the molecules. It's collecting data on all of the molecules that are moving around and recording an average of that. And so when things happen like ice melts, the temperature doesn't actually change because the molecules are all gaining energy in order to go from that solid state to that liquid state. And as they're all gaining that energy, the average temperature doesn't actually change. And so what we see happen is that as the ice is melting, the temperature remains at 0 degrees Celsius until all of the molecules have gone to the liquid state. Now, heat is a little bit different because heat means that that energy is actually being absorbed by those molecules, and they have to keep taking in energy and taking in energy. So heat is a value of how much of an energy, whereas temperature is an average of those molecules' movement. So to do these calculations, we are going to use an equation, which you can see here is Q is equal to M times C times delta T. So the first thing we're going to do is identify what all of these are. So Q is the amount of heat, and that is going to be in the units of joules, calories, or kilocalories. A calorie is equal to 4.184 joules, so we can see our relationship between these. And 1,000 calories is equal to 1 kilocalorie, and we use a capital C there, so we can see the relationship between these two there. So Q is an amount of heat, an amount of energy that the molecules have. M stands for mass. That's our first item in our product. Mass has to be in grams. C stands for specific heat. And we're going to learn a lot more about specific heat. Specific heat is how many joules of energy does it take for 1 gram of the material to change in temperature by 1 degree Celsius. So again, we're going to identify all of these again, and then change in temperature, delta T. We're always going to take our final temperature minus the initial or starting temperature. And we do always have to be in degrees Celsius. Now, we've already talked a little bit about specific heat, and specific heat is, again, how much energy do we need in joules to change 1 gram of the material by 1 degrees Celsius. So water has a very high specific heat. It takes, you can see 4.184, it takes that many joules of energy to change 1 gram of water by 1 degree Celsius. It's a very high specific heat. Most metals have a specific heat that's less than 1. So you can see that metals are going to heat very quickly, because it doesn't take as much energy. Metals are going to cool off very quickly, so they're going to stay warm for a shorter period of time. Water is going to be the opposite of that. It's got a high specific heat. Water is going to heat slow and cool slow. And we're going to practice that understanding of specific heat a lot. So here's our first practice problem. It says, how much energy is required to heat 120 grams of water from 2 degrees Celsius to 24 degrees Celsius? So first, let's identify all of our different pieces. It asks us how much energy. So that means we're going to want to solve for Q. Next thing, let's find our M. What is our mass of our material? Well, it says our mass is 120 grams. So that means that we're going to put our M as 120 grams. Then our C, specific heat. So remember, it says how much energy is required to heat water. So that means we're going to be looking at the specific heat of water. And the specific heat of water is 4.184 joules per gram degrees Celsius. Then we're going to calculate our delta T. Delta T is calculated by taking our final temperature minus our initial temperature. So it says we're going from 2 degrees to 24 degrees. So our final temperature is 24 degrees. Our beginning temperature that we started at is 2 degrees. So our change in temperature is going to be 22 degrees. Now we're going to put each of these variables into this equation right here. So our mass is equal to 120, our specific heat 4.184, and our temperature change 22 degrees. All we do is multiply each of those in order to get our answer. Let's try and set up another practice problem. Again, it says how much heat, and is asking us in kilojoules, so we'll talk about that in a second, is given off when 85 grams of lead, so there's our mass of 85 grams. It cools from 200 to 10 degrees Celsius. So keep in mind that our initial temperature is going to be this. It's starting at that, so that's your initial. Your final temperature is 10 degrees Celsius, so that's your final. And remember, delta T is your final temperature minus your initial temperature. So when I calculate my change in temperature, it should look like that. Sorry, I moved everything here. So it should be our final temperature is 10 degrees, and our initial temperature was 200. So yes, we're going to get a negative here. And if you recall, positive and negative Qs indicate exothermic or endothermic. So we'll review that as well. Then we do need the specific heat of lead, so we're given that. And so here's our specific heat of lead, okay? And now we can put all those numbers right into our equation right here. So we're going to take our mass of 85 and multiply it. I'm going to move these to show the answer. Our mass of 85, we're going to multiply it by that specific heat, and we're going to multiply it by negative 190. So we're going to get a negative answer here. And when you multiply all of that, you're going to get a negative answer of 2,083.35. Now, it wants it in kilojoules. So this right now is in joules. So we're going to go ahead and we're going to convert that to kilojoules by dividing by 1,000, because kilo is 1,000. And so we would have 2.083 kilojoules of energy there. I'm going to go through these next parts a little bit quickly just because there's some notes that we've already covered. So we already know that a combustion reaction is going to give off energy. And so how do chemical reactions create energy? Well, the energy is stored in the bonds, okay? And when the bonds are broken, that energy becomes available to us. And we already looked at that in the first semester. And so when we produce bonds, energy is used up. And sometimes we have excess energy that gets released as heat. So in a chemical reaction, it's all about the bonds, and that's where the energy is either being used up or being released from. We've also already covered endothermic and exothermic, so I'm going to go over this quickly. In an endothermic reaction, we're using heat from the surroundings. So things like sweating and refrigeration are going to be endothermic. Exothermic heat is being released to the surroundings. So things like a combustion exercise, those little hot mitts that you get to keep your hands warm in the winter time, and then exercise would also be exothermic. So real quick recapping, endothermic reactions, the kinetic energy is going to decrease the temperature. The heat will transfer from the environment, so we're going to absorb heat from its surroundings. The system is gaining heat. We do get a positive value for Q, and so our delta H is equal to Q. It's always going to be less than 0. So greater than 0. So that's how we get that positive Q value when we're endothermic. Our products are always going to be greater than our reactants. So if you remember in our PE diagrams, in an endothermic reaction, we start with our reactants down low, and then our products have more energy at the end than our reactants did. We've also already talked about exothermic reactions. Those exothermic reactions are the opposite of endothermic reactions. And so we get an increase in the kinetic energy and an increase resulting in a hotter environment. That means that we're releasing the heat to its surroundings. The system itself loses the heat. So we can kind of think about if we've got a chemical reaction happening in a beaker, the energy is leaving and exiting. We get a negative value for Q. So our delta H, which is the same as Q, is going to be less than 0 because we get that negative value. And our products are going to be less than the reactants. So in our PE diagrams, if you remember, our products at the end have less energy. So our reactants start up higher and our products are lower down. And we have less energy at the end. So I took this out of your slides just because we've already gone over it. So again, you'll want to pause it and just take a moment for yourself to review everything about an endothermic reaction that we went over. Look over the PE diagrams and everything I talked about reviewing that endothermic reaction from our last unit. This is also here as a review for you on exothermic. So again, take a moment, pause the slide for yourself, recap what those PE diagrams look like right here, how delta H is related, how the heat is released, meaning our delta H having a negative Q, and review that for yourself from our last unit. So enthalpy is kind of another word for heat. Our symbol is going to be H. When we're looking at delta H, which is the change in energy per mole, we're going to start to bring in some stoichiometry. So for us, our heat and enthalpy are going to be pretty much interchangeable. We're going to use this equation, Q equals mshot, mass times specific heat times delta T. I kind of abbreviate it as Q equals mshot. The system of energy for us is pretty much equal to delta H. Okay, so we're going to use delta H and Q pretty close to interchangeably. The only difference is that when we're talking about delta H, it's going to be per mole. And so this is where our stoichiometry comes into play. And so the key here is to keep in mind that it's energy per mole, and the Q of this system is per moles. And so we're going to see how that plays a role in a balanced chemical equation. We have a law that we see within these thermochemical reactions, and it's called the law of conservation of energy. And what this says is that energy is not lost or gained in a chemical reaction. It can't just simply disappear. If one system gains the energy, then the other system had to lose the energy. And so it simply gets transferred from potential energy to kinetic energy. And we're going to see that in our calculations. So now when we're writing chemical equations, we're going to include the heat change that we see. So when we write a thermochemical equation, we're going to include the delta H. So write this in, our change in temperature, or not our change in temperature, our change in heat energy is that we've got negative 65.2 kilojoules. So remember, if delta H is negative, it's exothermic, and heat is being released, which means that heat is a product. So when we rewrite this equation, we put that 65.2 kilojoules as a product. And what this tells us is that if we've got 1 mole of this material reacting with 1 mole of this material, we will produce this much energy as a product, and we will produce 1 mole of this material. So it is molar, there's a molar relationship according to our balanced chemical equation that we have there. So in this problem, we have tin metal can be extracted using a chemical reaction. So we have our balanced chemical reaction here, and we can see that energy